Hello students, and welcome to section 3-5, Scatter Plots and Lines of Fit. As usual, there is a model and discuss problem that I want you to take a look at on your own and try to see how these plotted data points can be modeled, possibly not necessarily in a linear format, because all these points will not fall on a single line. But in a sense, they are close enough to be on one line where they are averaged out, possibly where the line maybe could fall somewhere in between almost all points and maybe even go through a point or two as well. This particular we call scatter plot of points helps us frame our understanding to where certain data values could theoretically be modeled linearly. And that's going to lead into our example 1 for today. Understand association. What is the relationship between the hours after sunrise, X, and the temperature, Y, shown in the scatter plot? So we'll take a look. Temperature after sunrise in degrees Fahrenheit on the Y-axis, and on the X-axis, hours after sunrise. So you have time versus temperature. Now, all of these data points, as you can see, are scattered about in such a way where even if I try to draw a line through all of them, there's no way that I could do that. However, there is a trend. There is a trend of which you can see as the hours increase, the temperature also increases. We have a little bit of a dip here, and then we have almost a straight horizontal line off to the right after about 9 hours or so. The temperature is generally increasing over time. Now, I did say trend. The trend is, if I did make a line here, not of course going through all points, but if I did draw a line here, on average it would be a line that's trending up and to the right, or better yet, a line with a positive slope. As we continue, as the number of hours after sunrise increases, so does the temperature. When Y values tend to increase as X values increase, the two data sets have what we say a positive association. So these are positively associated, hours versus temperature. Continuing, part B. What is the relationship between the hours after sunset X and the temperature Y shown in the scatter plot? So if we continue here, we can go ahead and see the scatter plot yet again. Temperature after sunset in degrees Fahrenheit on the Y-axis, and again the X-axis, hours after sunset, and those take shape accordingly. We have points that as hours increase, you can see the trend of temperature values going down. The temperature is generally decreasing over time. So the trend, I would argue, would be, if in fact we kind of look at it linearly, the trend would have a negative slope. Again, not one line can go through all points, but that's the trend. As the number of hours after sunset increases, the temperature decreases. When Y values tend to decrease as X values increase, the two data sets have a negative association. Moving forward, part C. What is the relationship between the hours after sunset X and the amount of rain Y shown in the scatter plot? So yet another relationship, X versus Y. Rainfall after sunset, there it is in inches on the Y-axis, and then you have the X-axis as such, hours after sunset. Points are scattered about. If you can tell here, well, technically I can't distinguish whether or not these points are going to trend in a positive slope manner or in a negative slope manner. In other words, a positive association versus a negative association. I can't easily, if at all, draw a line generally or on average going through, generically the points as they're structured. There is no general trend in the data, we say. Because there is no relationship between the amount of rainfall and the number of hours after sunset, we say that there is no association. When there is no general relationship between X and Y values, the two data sets have no association. We could also say there's no trend really in the data, no general trend, like I said. Moving on, example 2. How can the relationship between the hours after sunrise X and the temperature Y be modeled? So if we take a look, says the data points on the scatter plot approximate a line. Sketch a trend line that best fits the data to determine whether a linear function can model the relationship. So here's our graph, temperature after sunrise. Okay, and you can kind of see here, like we've seen already on other problems, that there is a trend in the positive kind of direction, or there is a positive association. But on top of that trend, again, measuring hours versus temperature again, the trend line suggests that a linear function can model the relationship. The line in blue, again, not suggesting it goes through every single point, of course, but the line in blue is a trend line, again, that models, generically speaking, how this is taking shape. So I would argue that this is a, well, positive association, as it's described here, but also a positive correlation specifically. The scatter plot suggests a linear relationship. There is a positive correlation between hours after sunrise and the temperature. When data with a negative association are modeled with a line, there is a negative correlation. If the data do not have an association, they cannot be modeled with a linear function. Okay, so there is something to be said about a positive correlation given that trend line. A negative correlation giving a trend line maybe you could draw here in blue. And then of course on this graph, no correlation because there's no association. So those are the terms you need to be familiar with: positive correlation and association, negative correlation and association. And again, if there's no association, we say there's no correlation. Example 3. What trend line models the data in the scatter plot? So let's take a look at this. We can see here a trend line first models the data in a scatter plot by showing the general direction of the data. A trend line fits the data as closely as possible. Step 1, sketch a trend line for the data. Remember, a trend line approximates a balance of points above and below the line. I say remember, but I would argue that's pretty intuitive since, again, our line will not go through every single point. So it approximates a balance of points. In a sense, it's like an average. So we're going to compare electrical hybrid cars sold, where we look at the XY axis and the points plotted, as well as the blue trend line. Okay, so the year starting in 2000 versus the number of cars sold in thousands. So you've got a bunch of points scattered about, where I would argue these points are scattered in such a way where there's a positive association. The blue trend line, okay, is modeling the data by showing, again, the general direction. The trend line fits the data as closely as possible by approximating a balance of points. It's not obviously going through all, but it's balancing. The trend line might not pass through any of the data points. It may, or it may not. In this case, it doesn't appear that it touches too many points, if at all. Maybe possibly 2,50 if I look at it again, and 16,500. But some of those other points are not going to fall on the trend line, which is fine. That could very easily happen. Step 2, write the equation of this trend line. Speaking of those two blue points that in fact the line did go through, 2,50 and 16,500, go ahead and select those two in the context of then finding the slope. So y2 minus y1 over x2 minus x1, or 500 minus 50 divided by 16 minus 2. And that ends up being, as you can see, 32.1 if you do the math, roughly speaking. You can double check that. Okay, and then you use the slope and one of the points to write the equation in slope-intercept form. All right, in this particular instance, actually, they used point-slope form first. If you recall, point-slope form is y minus y1 equals m, slope from above, times x minus x1. Now, they chose 2,50 in context as x sub 1, y sub 1. They distributed the 32.1, and then they added 50 over, so that your y-intercept is negative 14.2 with a slope of 32.1. Slope-intercept form of the trend line is as such. Okay, so we can see here again that the trend line has a an equation format as such. It's modeling the data. Y equals 32.1, x minus 14.2. This trend line is one of many possible trend lines. Okay, I would argue that if you do pick two different points, because maybe your line, I don't know, maybe your line did go through this point right here, and maybe this point right here. Let's say you drew your line through those 2 points. That's not wrong per se. Just keep in mind that your slope better still be close to 32.1, and your y-intercept better still be close to negative 14.2. There are a variety of answers because, again, maybe you didn't pick this blue point and that blue point. Maybe you picked that red point here and that red point there. And if that were the case, you would use the same steps but using those 2 points. The equation should again be very close though. Roughly still 32.1 for a slope and negative 14.2 for a y-intercept. Let's move on. The table shows the amount of time required to download a 100 megabyte file for various internet speeds. Assuming the trend continues, how long would it take to download a 100 megabyte file if the internet speed is 75 kilobytes per second? So here's our data in an XY table format. We've got time to download versus internet speed. So 35, 6.65 and so on. 40, 5.82. Okay, as a matter of fact, it's internet speed versus time, as X and Y, I should say, specifically are designated. X is going to be internet speed in kilobytes per second, while Y will be megabytes, 100 megabytes per minute. So minutes, as we'll see here in a moment. Step 1, make a scatter plot of the data and sketch a trend line. So here's your scatter plot. Notice again we've got our internet speed on the x-axis and our time to download on the y-axis. The points are plotted accordingly, 35, 6.65 and so on and so forth. Okay, so all those points, 40, 5.82 and so on. Now they are choosing, after drawing the trend line, looking as such. By the way, this would, I would argue, certainly being a negative association, so a negative correlation. Negative association because it's a negative slope, so negative correlation again, we can argue. They are choosing, as it turns out, or will choose 40, 6 and 55, 4 in the context of the point slope form and then slope intercept from there. So step 2 again is to find the equation of the trend line. Select 2 points on the trend line to find the slope. 40, 6, like I said, and 55, 4. Now, they are rounding. I will argue that rounding is not ideal. I will argue that on this problem, that's fine, but when you do this on your own, it's probably a better practice to actually use, instead of 6, use 5.82, and instead of 4, use 4.23. They're getting away with that here, but that's okay. The slope, again, if you do the math, y2 minus y1, over x2 minus x1, so 6 minus 4 divided by 40 minus 55, you get a slope of about negative 0.13. Use the slope in one of the points to write the equation for the trend line again, noting that if you picked a point, which they picked 40, 6, using the slope of negative 0.13 and using y minus y1 equals m times the quantity x minus x1, simplify, distribute the negative 0.13, add 6, and you end up with this slope-intercept form. Continuing on, we can see here that the equation of the trend line is this. Step 3, use the equation of the linear model to find the value y that corresponds to 75 for x. So you'll finish by plugging into this equation 75. So negative 0.13 times 75 plus 11.2. And we can gauge then that approximately at 75 kilobytes per second, we're going to have 1.45 seconds in the end. And that should conclude how this linear model takes shape and predicting the value after this amount for x.